So the next talk will be by Pierbiagio Pieri from Camerino, yes, and we'll be hearing about mass imbalance effect in resonant Bose-Fermi mixtures. Thank you.
Thank you. I forgot. Can you hear me?
You have to turn on.
Oh, so sorry. Yeah, right. First of all, I also want to thank the organizer for giving me the opportunity to present our work in such a nice workshop. So thank you to Rudy and Carlos. So the work I'm going to present was done in collaboration with Elisa Frattini, who is sitting here in the audience. She's a graduate student at the University of Camerino, and she's going to finish at the end of this year. In the last part of the talk, I will also present some results, which are preliminary, and that were obtained in collaboration with Gianluca Bertaina and Vincenzo Savona from the EPFL in Lausanne, Switzerland, and Stefano Giorgini, who's also here, from Trento University. Okay. So let me, first of all, I want to give a brief overview of where are we now, maybe where we were before the last two presentations with Bose-Fermi mixtures. So quantum degeneracy with Bose-Fermi mixtures has been obtained so far for several systems. The idea is that this list is exhaustive, but I'm not so sure. So there are many different mixtures that have been obtained so far, and some of them are tunable in this. Well, one listed in blue. Some of them are isotopic, so with essentially the same mass for the atoms which are involved, while others have even very large mass ratios between the boson component and the Fermi component. What has been observed so far in this mixture? Well, first, initially, essentially people observe the collapse of the, especially with the rubidium-potassium mixtures, and this was observed especially in non-resonant mixtures. Then Feshbach molecules were created both at Gila and at Hamburg with a resonant rubidium-potassium mixtures, and now also with the sodium-potassium mixtures they have been created at the MIT. In these mixtures, triatom losses are certainly a difficulty because they produce this loss rate. However, these loss rates are proportional to the square of the density of the bosons times the density of fermions. So, in principle, working with mixtures with a majority of fermions with respect to bosons would help in avoiding, in reducing this loss rate. Okay, what about theory? Theory, stimulated by the experiment, initially concentrated on the study of the collapse mixtures and phase separation for non-resonant mixtures. This was about the year 2000. Then at around the year 2005, people started looking for resonant Bose-Fermi mixtures, but all of this initial work were done by Sachdev, Stuf, Marchetti and collaborators. All of this work concentrated on narrow resonances. There is a reason for that, because for certain in certain respect, a narrow resonance simplifies some calculation if the resonance is very narrow, okay? Because then you can apply the kind of a mean field. And so, and in particular, you have a small parameter to work with. In this context, the possibility to have a quantum phase transition associated with a complete depletion of the condensate due to the increasing pairing correlations which want to produce fermionic molecules was examined, in particular by Sachdev and co-workers. Recently, the case of a broader resonance has also been studied in some works, including ours. So in this work, we consider the Bose-Fermi mixtures in the presence of a wide Fano-Feshbach resonance. We assume the density of the fermions to be larger than the density of the boson for two reasons. The first one, the theoretical one, is that we are interested in studying this quantum phase transition associated with a complete depletion of the condensate. And this phase transition is a phase transition only when the density of fermions is larger than the bosons. Basically, because if you have if you have more bosons than fermions, then there will remain some bosons that are not paired into molecules, and t equals 0, they will be condensed. The second reason is that, for sure, free atom losses, especially if the boson concentration is small with respect to the density of the fermions, free atom losses will be much less problematic. So our system is described by, since the Fano-Feshbach resonance is broad, is wide, can be described without taking into account closed channel molecules. So it's described only in terms of fermionic and bosonic degrees of freedom. Bosons and fermions are coupled by a contact potential, which can be parameterized in terms of the boson-fermion scattering length. And we assume the interaction between the boson itself to be repulsive for stability reason, but weak, in such a way that we can describe it as a simple mean field shift. So this simple mean field shift is reabsorbed into the chemical potential of the fermions and bosons, but the presence of this repulsion is certainly useful for the stability, overall stability, mechanical stability of the system. So we use many-body diagrammatic theory. We consider the interaction between, we describe the interaction between fermions and bosons within a T-matrix approximation. So I don't want to enter into the details, so these are the diagrams that we use. The rationale behind the choice of this self-energy, T-matrix self-energy, is that it recovers the correct weak coupling and strong coupling limit. So strong interaction and weak interaction. For a weak interaction, we have dilute weakly interacting Bose-Fermi mixtures with a mean field shift of the chemical potential, which is proportional to the boson-fermion scattering length. While in the strong coupling limit, we recover the description in terms of molecules, which are described by this propagator, which in the the strong coupling limit goes into this, has this structure. Molecules coexisting with unpaired fermions, okay? Because we're assuming, as I told you, the density of fermions to be larger than the density of bosons, or at the most equal, at the least equal. So within this theory, so we concentrate on the normal phase and we lower the temperature and we want to look at the condensation critical temperature. So in this plot, I'm reporting the condensation critical temperature versus the dimensionless coupling strength, which is essentially the inverse of the scattering length times the interparticle distance. We use this fictitious Fermi wave vector, which is defined in terms of the overall density, as if the bosons were fermions. So you can see from this plot that when the interaction increases, the attraction between bosons and fermions increases, the critical temperature decreases and eventually vanishes at a critical point, which should be the position of this quantum phase transition. The different curves correspond to different concentrations of the bosons with respect to the fermions. Okay? You can see that from this plot is for equal masses. You can see from this plot that the position of the quantum phase transition looks quite independent, or weakly dependent, is more correct, on the density ratio. So this weak dependence on the density ratio remains also for systems with different masses between bosons and fermions. So in this plot, on this axis is here we are using the density imbalance. So anyway, so we are ranging from 0 boson density to boson density equal to the density of fermions. And you can see that the curve is very, very flat. On the other hand, there is a quite sizable dependence on the mass ratio. The critical coupling depends quite strongly on the mass ratio. So on the next slide, I'm showing the behavior of this critical coupling as a function of the mass ratio for different values of the concentration of the bosons with respect to the concentration of the fermions. So I'm presenting two pictures. On the left, the boson mass is less than the fermion mass. On the right, is larger. So you can see that the critical coupling associated to the disappearing on the condensate increases quite rapidly by decreasing the boson mass. Okay, so with the light bosons, the critical coupling is shifted to stronger and stronger values. Okay. On the other hand, on this side, so for bosons heavier than the fermion, the critical coupling depends less on the mass, has a dependence which is slower. It's rather flat with a minimum for intermediate values of the mass ratio. There is a minimum at about between 4 and 5, depending on the concentration of the bosons with respect to the fermions. But eventually, also for large mass ratio of the bosons, this critical coupling increases. So we try to understand this, and so we have considered the specific limit where the boson density is let to vanish. So in this limit is a single boson surrounded by a Fermi sea, but a single boson is like a single fermion, so there's no difference, like a single spin down in a Fermi sea or spin up. So we are in the same limit that was studied for the polar molecule transition in Fermi gases. In this limit, one can do an analytic calculation within this geometric approximation And one gets that the critical coupling diverges for small boson mass in this way, so it's inversely proportional to the boson mass. This is the leading term. This is a subleading correction. While the boson mass is much larger than the fermion mass, the critical coupling increases, but it increases with a logarithmic law, very slow. And actually, I should say that this asymptotic behavior, where I have included already a subleading term, is very, very, very asymptotic. Okay, so one should include also we had also the subleading correction to this behavior. So, but anyway, the critical coupling increases also in this situation. So the idea is that since there is a rather small dependence on the density imbalance, the behavior of the single boson essentially determine the behavior of the single boson problem surrounded by a Fermi sea, determines essentially the behavior of the mixture, also at a finite boson concentration. Now let's consider the momentum distribution function. This is t equals 0. Let's first consider the fermionic distribution function. So now I consider a mixture where I have certainly more fermions than bosons. Okay. It is quite apparent from this picture that there is a kind of two-component behavior in this momentum distribution function. There is a Fermi gas of the ampere fermions, which fill their own Fermi surface. So this is the Fermi surface of the ampere of the excess fermions. So we can see the Fermi step at a value which is determined by the difference between the fermion and the density and the boson density. After this step, so this is a magnification of this region, the y-axis, is rescale the y-axis. After this, there is this component. So the large momentum behavior is essentially determined by the internal molecular wave function, the square of the internal molecular wave function, modulo square, times the boson density, that is the molecular density. This for momentum larger, of course, than the Fermi momentum of the ampere fermions. But the boson distribution is more interesting. The boson momentum distribution is more interesting, in my opinion. This is the boson distribution. Here is plotted at the critical coupling, but it is not important to be at the critical coupling. It's sufficient to be on the molecular side. Okay, so also in the strong coupling, also this is a case where, for instance, where the coupling is larger than the critical one. So you can see that there is an empty region in the bosonic momentum distribution, completely empty. The reason for this behavior in momentum, for this quite strange at the beginning momentum distribution, is simply due to the effect of the Pauli exclusion principle for fermions on the bosons. In what sense? We have a Fermi surface, a large Fermi surface. We are considering a case where the boson density is less than the fermion density. So we have a large Fermi surface of the ampere fermions. So all the momentum state with the momentum less than the Fermi wave vector of the ampere fermions are occupied by fermions. Then the bosons want to pair with fermions to form molecules. But they can pair only with fermions outside the Fermi surface of the ampere fermions. Okay? So the momentum of the fermions should be larger than this Fermi wave vector of the ampere fermions. However, the molecules here are composite fermions. So the molecules fill a Fermi sphere with a Fermi momentum, however, which is small because the density of boson is rather small. So this means that the boson, since the momentum of the molecules is the sum of the momentum of the boson plus the momentum of the fermions, this means that the momentum of the boson, when the momentum is less than the difference between the Fermi momentum of the ampere fermions and the momentum of the molecules, these states are not allowed. Are not allowed due to the Pauli exclusion principle on fermions, which indirectly acts on bosons. So I found this this behavior quite interesting, because we are seeing the effect, many body effect, because it's produced by the presence of a Fermi surface of the other fermions, on an almost two-body quantity, because this is the molecular wave function, but with the constraint. It's the two-body, if you want, equation solved in a subspace where a part of the Fermi space is forbidden. Okay. Okay, this is the evolution of this bosonic momentum distribution as a function of the concentration of bosons. So you see that essentially at a certain point this is completely filled. It is possible to derive, we have derived an expression for this distribution of momentum in the strong coupling limit, which has this, is given by this equation for very strong coupling. From this equation one understands immediately, can get the shape of this curve. Okay, so now I want to present some preliminary results that have been obtained with the fixed node diffusion Monte Carlo in collaboration with Gianluca Bertaina and Stefano Giorgini and Vincenzo Savona. Okay, so let's concentrate on this plot. There are many curves, but let's concentrate on the blue one and the red one. Okay, the blue circles and the squares. So what I'm presenting here is the energy as obtained by the fixed node diffusion Monte Carlo, but using two different trial wave functions for fixing the nodes of the fermionic components. We have used, let's say, weak coupling trial wave function, which is made by Slater determinant for free fermions, multiplied with a Jastrow correlation factor between bosons and fermions. Here it is plotted the energy. Better, it is the energy minus the binding energy of the molecules when the scattering length is positive, multiplied by the concentration, in order to subtract a trivial part from this plot. So this is the behavior of this of the minimization obtained by starting with this weak coupling trial wave function. On this side are the results for the energy obtained with a different, completely different trial wave function. It's a trial wave function which is which contains the physics of the dimers of the molecules which are formed. It's made by the product of two Slater determinants, one for free ampere fermions and the other one for these composite fermions, these molecules. And the bosons, with all the bosons residing within the molecular orbitals. You see that the energy obtained for the two curves crosses, the two energy crosses at a coupling of the other one for this concentration on bosons. And this crossing could tentatively be identified with the position of this of the quantum phase transition that I was that we have looked before with the T-matrix approximation. A check of the goodness of the calculation in the strong coupling limit is provided by comparing the energy, this energy, with the energy obtained for a mixtures of molecules and fermions interacting each other with the scattering length, which is given by 1.18, this number which comes from three-body physics, is 1.18 the scattering length for the Bose-Fermi. So you see that there is a quite good agreement. And the last curve, since I was excited by the distribution momentum function for the bosons, in particular for the presence of this empty region in the boson momentum distribution function, here I'm showing you a comparison with result obtained by the Monte Carlo methods, a comparison with the T matrix for a coupling which is rather strong. And you see that as far as the momentum distribution function of the bosons is concerned, the agreement is pretty good. The point is that this quantity is not sensitive. It's not very sensible, for instance, to the correct value of the molecule fermion scattering length. Within our theory, within the T matrix approximation, the Bose-Fermi scattering length is treated in an approximate way. One recovers the so-called Born approximation value for this. So one get a different number from 1.18. Get 8/3 for equal masses. I forgot. This is for equal masses. Okay. But for this quantity, this is not so important. This is a second-order effect. The leading effect is this effect of the Pauli repulsion due to the presence of a large Fermi surface of the ampere fermions, and so this is captured very well by the T matrix. Okay, so yes, I think I'm done. So these are our conclusion. So we have seen that for broadly resonant Bose-Fermi mixtures, one has the same transition that was first examined in the context of narrow resonances. We have found an interesting behavior of the momentum distribution function for the bosons that, in principle, I think it should be measurable. Well, Martin maybe would want to comment on that, but because it is in a regime where it should not so well. It's not necessary to be close to the resonance. Okay. One has this already in the molecular regime, even away from the resonance. Okay. So in this way, one could observe this effect of Pauli exclusion on the boson occupancy. The preliminary result of fixed node diffusion Monte Carlo calculation confirm such an overall picture. What I left aside from this discussion is the competition with phase separation, and this could be an issue. The competition with phase separation could oversee this quantum phase transition. So the transition could become a first-order transition, okay, and so it could be. In this way, it would be impossible to follow completely the transition up to the point where the condensate goes exactly to zero. However, my hope is that since there are many parameters here that one can use, so different masses, different repulsion between boson and boson, different trapping frequency, that there could be a regime where phase separation could not spoil the presence of this quantum phase transition. Okay, that's all, and then thank you.
Thank
very much for this talk. Questions?
How did you define the critical point to extract the critical temperature, or at zero temperature the critical coupling? Somehow I missed that point.
Yes, you're right. Yes. The criterion for the critical temperature coming from the normal phase in our theory is when the boson chemical potential equals the boson self-energy at zero momentum and zero frequency. Okay, it's the same. Is the extension to an interactive system of mu b equals 0. The same criterion is used at t equals 0, coming from the normal phase.
I understand. Just a brief question. The term you neglected in the energy, the self-energy of the bosons with themselves, depends on the chemical potential.
Okay.
And this might have an additional contribution in view of this criterion.
Okay. You mean the boson-boson interaction. So the boson-boson interaction is assumed to be weak in such a way that it can be treated as a mean field shift. So this mean field shift will be a shift of the chemical potential, a rigid shift of the chemical potential, and what will not change at all. This it's like for the Bose gas. If you calculate for the pure Bose gas, the shift on the critical temperature, if you include only the mean field shift, the critical temperature doesn't shift. Only in a trap is shifted, but for different reasons.
Okay, further questions? Carlos?
Yeah, so you mentioned about phase separation, but you mentioned about phase separation. Yeah, have you computed?
Compressibility.
Yes.
The compressibility is positive definite. In our so
your system is mechanically stable.
It's
then.
mechanically stable, but
so you worry about phase separation coming from what kind of mechanism?
well, because this is not sufficient. I mean, it's a local stability criterion, but if you let the system to have the possibility to occupy, let's say, different, to split into different regions, volume, you can minimize your energy.
No,
the compressibility would be positive everywhere in the space. I would agree with you that you would not have.
No, but so that just means you have not explored enough yet. But
no,
as long as you have
not explored the condensed phase. Okay?
Oh, okay.
Coming from above.
From above. Okay, I got it.
Okay, further questions? Matteo.
Sorry, it's very interesting, but I think I don't get this graph.
Yes.
Can you re-describe what is this exactly? Yes?
Is the critical temperature for the condensation of the bosons, okay?
Yeah.
Y-axis. On this axis is the coupling strength between boson and fermions.
Yeah.
And the different curves are for different boson concentration. The critical temperature is normalized to this Fermi energy, okay?
Actually, I mean, concerning the points where it goes to zero, so you actually see that the lower is the concentration of bosons.
Yes.
The
lower this critical temperature? No, what?
The lower is the coupling strength.
Okay, on concentration, the critical coupling depends very little on the concentration. You see that it's only it varies only here.
But this variation, I would expect that depends, however, on the scattering length you have chosen for the boson-boson interaction, or?
Okay, no, as long as the boson-boson, okay, so your question is why the boson-boson interaction does not appear at all in this plot, in a sense. I have only this parameter. As long as the boson-boson repulsion can be treat it only as a mean field shift. So if it's if the boson component is dilute, the gas parameter for the boson component is small, this is not affected at all by the boson function because it's only a shift.
Okay.
The boson, okay.
Yeah. And sorry, the other graph, I think the next slide or so where you evaluate with the with the Monte Carlo.
Okay.
Yes, this one. I mean, do you recover in the limit of very small concentration of bosons, this polar onto molecule crossing that one can evaluate
Okay.
in easy way?
In principle, it should be recovered, of course, but for the calculation were not down to this limit. So we only a few. These are preliminary results. So only a few values of this concentration were explored. Okay, but this value is quite close. This critical value is very close to the position of the polar molecule transition. Yes. So in this sense.
But the position you had in the former treatment was different. So that was more 1.6.
Yes, exactly. So the question is, there is while in thematics we get 1.6, while from quantum Monte Carlo we get about 1 for this. This is due to the fact that the thematics overestimates the repulsion between the molecule and the fermions, because it gives a value of the scattering length of the Bose-Fermi scattering length which is very large. Actually, it is essentially this is if one look at the energy on the variational wave function before letting the diffusion to decrease. This is the energy that one gets and is compared with the value of the Bose-Fermi scattering length in the Born approximation. Okay, so essentially it is this upper shift of the molecule energy that make the thematics less convenient the molecule formation. So it shifts the coupling strength to larger values with respect to Monte Carlo. Yeah.
So in the Monte Carlo calculations, the turnaround of the blue points, is that a real effect, or is that just because it's an upper bound?
No, I think that this is in this region, the wave function that you are using, you are enforcing your system is starting to feel the fact that it's unphysical. Okay, that is not that the nodes of the wave function are not the good ones. So I would not. I don't know, Stefano, if you want to comment on that. I don't know. I would not believe that this is physical. I mean,
but
one would have. I guess that if the quantum phase transition would be second order. Actually, you should not have a crossing of the energy, okay? You should have a continuous evolution of the energy with just, okay? Of course, the fixed node diffusion Monte Carlo makes the transition by construction first order, in this sense, because here are compared to the result obtained with two different trial wave functions. No?
Just a
Yeah.
follow-on question. So if you
Wait a second.
if you don't sort of fully believe that crossover, how can you interpret the crossing point as being the critical point?
No, I mean, the answer is the following. Beside this question mark, is the following: is that we are calculating the condensate fraction. We are still calculating the condensate fraction on this part. And ideally, we should follow the behavior of the condensate fraction and look if the point where you can extrapolate the condensate fraction to vanish would be in agreement with the position of this critical coupling that is obtained by this two-wave function. But of course, in this region, you should have an even better with the tri-wave function in case you have the correct physics. I don't know, Stefano, if you.
Yeah, so, well, so first of all, those are very preliminary calculations. There are still some issues that we would like to understand better, like what happens. For example, for bosons, we use hard sphere repulsion to model the interaction between bosons. So we would like to understand what is the effect of finite range effects and so forth. But then, so concerning the calculation, so that's very so clear in a way. So you are comparing two homogeneous systems, one made up with so you have a free gas of fermions and then bosons that interact with the fermions. And so if you follow the blue branch, you always have a condensate fraction associated to the bosons. And instead then on the red branch, you have no condensate fraction because the bosons are paired into fermions and then fermions obey the Pauli principle. And so for us, so it's clear that you have two different nodal surfaces for the two wave functions, and so this gives you two different energies, and you can compare when one is better than the other. And then there is no surprise that at some point you have a crossing. Okay. So, but then, as Pierbiagio was saying, of course, then you should consider the possibility of having phase separation. So, probably, so it could be that, so you at some point you have a phase separation between a phase where the two densities of bosons and fermions are different, and so you don't see this crossing, and you have a first-order phase transition.
Okay, thank you. If there are no urgent further questions, I think we move to the next speaker. So we thank Pierbiagio